After completing this chapter, the learner will be aware of the environmental and health risks associated with bunkering operations. Know the requirements prior to commencing bunkering operations. Know the startup procedures for bunkering operations. Know how to carry out bunkering operations, including topping off. Know the requirements for sampling and testing of the fuel, including the relevant sections of MARPOL Annex 1 and Annex 6. Before we start to look at the actual bunkering requirements and procedures, it is worthwhile looking first at the hazards that are present during bunkering operations. This will help to explain why some of the procedures are in place. As we have already mentioned, the ISM code is intended to ensure safe operation and pollution prevention. The ISM code requires that companies and the ships that they operate have a safety management system in order to comply with the code. The safety management system should cover all on-board operations which have an identified risk or hazard potential, as well as identifying responsible persons and reporting and auditing procedures. These should be contained in the Safety Management Manual, a copy of which must be placed on board the vessel. The potential risks and hazards to personnel, the vessel and the environment are particularly high during operations such as bunkering. It should therefore be obvious to you that these operations will be covered by the procedures contained within the Safety Management Manual for your ship. You should always familiarize yourself with any procedures for all operations that you are involved with on your ship before starting the operations. The main hazards during bunkering operations concern health and safety of personnel, fire risk, and environmental damage. Click on the buttons to learn more about each of these. It is important that all personnel involved with the handling and use of fuel oil on board ship are familiar with the relevant material safety data sheets for the grade of fuel concerned. The material safety data sheet will give detailed information as to the hazards and risks associated with the particular fuel, including important health information and recommended treatment of victims. The main hazards to health when dealing with fuel are skin contact, eye contact, vapor and gas inhalation, including the possibility of toxic gases such as hydrogen sulfide or benzene, and fuel ingestion. Using the appropriate personal protective equipment and being careful is the best way of avoiding injury or health problems for you and your fellow crewmen. As a minimum, you should use barrier cream, gloves and overalls to prevent skin contact, goggles to prevent eye contact, face mask or respirator, and minimize time at tank openings to limit inhalation risk. And use face mask and care when connecting or disconnecting hoses to limit ingestion risk. Flammable vapors are given off by a fuel once it reaches a temperature above its flash point. The flash point is defined as the temperature at which the vapors given off can be ignited by an external ignition source. When fuel vapor is mixed with the required amount of oxygen to form a flammable mixture and an ignition source is present, then fire or explosion can occur. A flammable mixture has a concentration of vapor between the lower explosive limit and the upper explosive limit. For hydrocarbon vapors, this is taken as approximately 1% and 10% by volume, respectively. To prevent a fire or explosion, it is necessary to either avoid formation of a flammable mixture or remove any possible ignition source. Marine fuels are required to have a flash point of not less than 60 degrees Celsius, although some vapors can still be given off below this temperature. Marine oil pollution has a detrimental effect on the environment and the local ecology, harming marine life and seabirds. Major oil pollution incidents usually result from groundings, collisions, etc., and involve either tankers or vessels with large bunker capacities. You will be familiar with many of these from reports on television and the newspapers. Incidents due to bunkering operations, although not usually involving large quantities, can still, however, cause a great deal of environmental and ecological damage. This is due to the fact that most bunkering operations are carried out either in port or in near coastal waters. Every effort should be made to avoid spillages, leaks, and overflows whenever bunkering, and all steps should be taken to minimize the effect of any such incidents should they occur. Bunkering procedures should therefore not only include good operational practice to prevent these incidents, but also contingency measures should they occur. We will look in greater detail at these procedures later in the module. Some shipping companies still leave the quantity calculation and ordering of fuel to the chief engineer on board the ship. In other cases, the fuel is ordered either directly from the relevant department within the shipping company office or by the charterers who have hired the ship. Whichever is the case, it is important that the correct grades and quantities of fuel are ordered to suit the machinery fitted on board and the operational requirements of the vessel. It is also important that the vessel has the storage capacity and tank configuration to allow the quantity of fuel ordered to be received and stored in a way that avoids operational difficulties and pollution incidents. So, even if the bunkers are ordered by onshore personnel, the person responsible for the fuel on board, usually the chief engineer, will need to plan where it is to be stored. He must therefore be able to calculate the fuel remaining on board and also plan which tanks will be used for the new bunkers in advance. To ensure that the correct quantity and type of fuel is on board at any particular time, it is necessary that bunkering operations are planned correctly. If it is left to the chief engineer on board to order the bunkers, the bunker plan will have to be drawn up based on information about the expected trade pattern of the vessel. He will have to take into account various factors when calculating quantities and forming his bunker plan, such as voyage length, vessel speed requirements, and therefore expected fuel consumption rate, required fuel reserve, legislative restrictions, and available storage capacity. In addition, he may have to take into account other factors, such as charterers' requirements and cost and availability of fuel at future ports of call. Once the required quantity has been calculated, then the fuel can be ordered. The required grades of fuel are selected by making reference to the specification in the current edition of the ISO 8217 fuel standard, plus any company and engine manufacturer's recommendations. The ISO 8217 fuel standard, which is covered extensively in the CBT number 179, Marine Fuel Properties 2, is the international standard for marine fuels. Many shipping companies have additional standards for their vessels. These take into account the treatment facilities on board and past service experience with different fuels. These company standards often have specifications not included in the ISO 8217 standard. The engine manufacturer's recommendations will take into account specific requirements for their engines, with particular reference to design limitations and service experience. You should try and make yourself aware of the content of ISO 8217 and also any specific requirements that your company or the engine manufacturer has for the fuel for the machinery on your current vessel. This will help you understand the handling and treatment requirements, and will also highlight possible problems you may have when using the fuels on board. Different grades of fuel may be required for the various machinery and equipment fitted on board the vessel. Even for those vessels using the same fuel for all of the machinery on board, it will be normal to carry 3 grades of fuel to meet different operating conditions. You should be aware that current air pollution regulations contained in MARPOL Annex 6 limit the level of sulfur allowed in marine fuel, with a reduced level in sulfur oxide emission control areas, often called SECARs. MARPOL Annex 6 has timetables for the reduction of the maximum allowable sulfur content in fuels both inside and outside SECARs. National legislation, for example within European Union countries, may require even lower sulfur levels. It is therefore important that the vessel's trading pattern is taken into account when selecting the grades of fuel to be bunkered. If the trading pattern of your vessel includes operation within a SECAR, a quantity of low sulfur fuel will have to be carried on board. This may also be the case if the future trading pattern of the vessel is uncertain. This will normally be in addition to the regular grades of fuel required, as fuel tends to become more expensive as the sulfur level is reduced. The different grade requirements will dictate the storage arrangements on board the vessel. It is recommended that fuels from different sources, particularly residual fuels, should not be mixed in storage. In other words, new bunkers should not be loaded into a tank containing any of the previous bunkers. The purpose of this recommendation is to minimize the risk of fuel compatibility problems, which may result in the formation of sludge and heavy deposits either in storage tanks or in treatment equipment. Mixtures of residual fuels can become unstable, even if the original fuels were stable, so mixing should be avoided whenever possible, as was stated in an earlier chapter. In practice, this is not usually possible, since fuel tanks are not normally completely empty unless they have been manually cleaned. They should, however, only contain the minimum quantity of old bunkers before filling with the new batch. Click on the buttons for more information about the different fuel grades in use. As already stated, MARPOL Annex 6 requires that ships have to operate the machinery on low sulfur fuel, LSF, in some areas. This requirement has brought with it many problems for the ship operator, such as supply, storage, and recording of the use of these fuels. Some existing onboard storage and transfer arrangements have had to be altered to allow storage of low sulfur oil, so that vessels can comply with these requirements. You should check the onboard arrangements on your vessel when you get the opportunity. The use of distillate fuels in main propulsion and many auxiliary diesel engines has decreased over recent years due to the high cost of these fuels. Many engines are now designed to operate on residual heavy fuel. However, some auxiliary engines, as well as some medium-speed main engines, still use distillate fuel all of the time. Even when residual fuel is the main fuel, there is still a need to carry some distillate fuel, either diesel oil or gas oil, for operation when, for example, heating facilities are temporarily unavailable for the heavy fuel. The grades of marine distillate fuels are detailed in the ISO 8217 standard for distillate fuel oil. The actual grade required for any particular engine is identified from this standard by the engine manufacturer. The ship owners may also have their own specification for fuels used on their vessels. Heavy or residual fuels are now commonly used for most main propulsion diesel engines. It is also an advantage, as far as storage and treatment requirements are concerned, if the auxiliary engines use the same grade, although this is not always possible. The grades of marine residual fuel are detailed in the ISO 8217 standard for residual fuel oil. Again, the actual grade required is usually specified by the engine manufacturer and the ship owner. Although these fuels are cheaper than distillate fuels, there is often an increased maintenance cost associated with using them, since the quality is generally not as good. You can check which fuels are recommended for the engines on your ship by looking in the engine manuals and any company instructions held on board. There are some potential operational problems that you need to be aware of when using low-sulfur fuels. Normal cylinder oils, which have high alkalinity levels, are not suitable when burning these low-sulfur fuels. The excess alkaline additives can lead to liner, piston ring and piston scuffing due to the deposits left after combustion. It may be that your vessel now has to carry different grades of cylinder oil to suit operation on these fuels. There is also some concern that the low levels of sulfur will affect the fuel's ability to lubricate the fuel injection equipment properly. This may require additional lubrication arrangements to be provided. You should check the onboard arrangements on your vessel when you get the opportunity. Although many vessels are now equipped with remote reading contents gauges for the fuel tanks, it is still good practice to sound the fuel tanks using a sounding tape to check actual fuel quantities. Every vessel is provided with tank capacity tables. These can be in a booklet or installed on the ship's computer system. These tables contain the information to allow the user to establish how much is in the fuel tanks for any condition of the vessel. Fuel is generally ordered by volume, so the tables are usually in cubic meters. You can use the density to calculate the mass of the fuel if necessary. Using the sounding tape, we can measure how much fuel is in the tank in one of two ways. The actual depth of fuel in the tank, a sounding, or the distance from the top of the sounding pipe to the surface of the oil in the tank, an ullage. It is unlikely that the vessel will be sat in the water without any list or trim, or that the fuel will be at a standard temperature when the soundings are taken. You will need to make corrections for this. Click on the buttons to see how we can calculate the ROB and correct for ship condition and fuel temperature. In order to determine the amount of fuel required, we need to establish how much fuel the vessel already has on board. This is normally referred to as the fuel ROB, the fuel remaining on board. You will probably have been involved in getting some of the information necessary for this by taking soundings of the fuel tanks. Once the tanks into which you will be loading the fuel have been identified, soundings or ullages are taken. The amount of fuel in the tank can be read directly from the table using these readings. The amount of fuel required is calculated by subtracting the fuel ROB from the amount we wish to have on board after bunkering. To minimize the risk of spillage due to overflow of tanks, it is common practice to limit the final amount in any tank to between 95% and 98% of total capacity. If the vessel is not at even keel in the water, the sounding or ullage will change as the contents of the tank shift. During the calculation, a correction needs to be made to take account of any list or trim. The trim can be worked out by taking the draft at the bow and the stern and subtracting them. The list can be obtained from a pendulum-type instrument known as an inclinometer, which is usually placed at the ship's centerline. This information, together with the tank sounding or ullage, can be used with the correction tables or input into the computer program to obtain the correct quantity in each tank. You can try using the correction tables on board your vessel to see the effect on the calculated quantity of fuel in a tank for different conditions of list and trim. The volume of fuel within the tanks, and therefore the level, will vary with the temperature. Like most substances, the fuel will expand as the temperature rises. It is therefore necessary to correct the calculated quantity of fuel in the tank for the actual temperature at the time the sounding or ullage was taken. Once again, this will be done either with correction tables or computer software. You can try using the correction tables on board your vessel to see the effect on the calculated quantity of fuel in a tank for different temperatures. There are a number of specialist bunker software packages available which can be used to assist in bunkering operations. One of these, produced by Shell, is the Bunker Calc package. This allows various calculations to be carried out automatically by inputting common fuel parameter values. You can see which calculations can be done by clicking on the 9 middle icons at the top of the picture of the Bunker Calc front page shown here. Now click on the button to see an example of one of the calculations available. The example shown here is for the calculation of specific energy. The first page shows the blank form for the required parameters. These are density, water content, ash content, and sulfur content. The values are entered into the form as shown on the second page. By clicking on the indicated icon, the calculation is done automatically. The third page shows the results displayed for both gross and net specific energy. If you have this package, or a similar one, on board, you should experiment with it to see the full range of calculations possible. Bunker Calc and other similar programs can be found on the Internet. As stated previously, every effort must be made to avoid fire and pollution incidents during bunkering operations. To ensure that this risk is minimized, a bunker checklist should be used. IMO and ISCOT have both produced examples of bunker checklists, and many operators either use these or have their own based on these formats. This will probably be part of the ISM procedures that you should follow. As stated earlier in this section, you should familiarize yourself with the procedures for your vessel before operations begin. The bunker checklist should include all of the actions that are necessary to avoid pollution from leakages or overflows and to minimize the fire risk. It will also include preparation of the equipment necessary to deal with any spills. It is essential that the communication methods between crew members and personnel from the suppliers are correctly set up and clearly understood. This should include an agreed procedure for emergency stopping of the bunkering operation in the event of any pollution or fire incident. No smoking notices should be posted, and the red signal flag raised to show that bunker operations are underway. When taking or transferring bunkers, every effort must be made to ensure no spill occurs, and that if it does, it is contained on board without causing a pollution incident. The various preparations that you must make and the procedures you must follow will be indicated on the bunker checklist for your vessel. On deck, there are certain preparations and precautions necessary before bunkering starts to minimize the risk of a spill and to contain any spill that may occur. These are listed here. Set all valves and lines to ensure delivery to correct tank. Fit all deck and save all scupper plugs and covers. Position any portable drip trays correctly, and prepare SOPEP equipment for use. Click on the button to find out more about SOPEP. All oil tankers over 150 gross tons and other ships over 400 gross tons are required to have a shipboard oil pollution emergency plan. Ships over 150 gross tons carrying noxious liquid substances, for example chemical tankers, are required to have a shipboard marine pollution emergency plan. These plans contain the actions and procedures which are considered necessary to avoid or minimize pollution in the event of a spillage or other incident. The equipment necessary to achieve this should be stored in a separate locker, clearly marked for this purpose. When taking bunkers, the equipment is prepared for use prior to start of the bunkering operations. One section of the bunker checklist will normally include SOPEP preparations. You should make yourself aware of the location and use of the SOPEP equipment on every vessel you work on. As well as any SOPEP requirements, the equipment needed to collect fuel samples is also made ready at the bunker manifold. We have seen that one of the items in the SOPEP section of the bunker checklist is to check the lineup of valves in the fuel transfer system. The valve positions required are usually included in the bunker plan for a particular bunkering operation. This plan should be used as a guide and checklist to ensure that the lines and valves are correctly set so that the fuel goes to the intended tanks. Although much of the bunkering operation will take place on deck, there will be some preparations necessary in the engine room. The actual engine room requirements will vary from vessel to vessel, but the items shown in the list may need to be considered. It is likely that engine room personnel will be involved with taking soundings and ullagers, as well as monitoring progress throughout the bunkering operations. This will include topping off and changing over tanks. Communication with the bunker supplier before and during the bunkering operation is very important. The supplier should provide a bunker delivery note with full details of the fuel specification prior to bunkering, and material safety data sheets for the fuel should be available. This should include a statement of MARPOL Annex 6 compliance. Before starting bunkering, agreement should be reached with the supplier regarding the required flow rates for starting, bulk delivery, and topping off. It is also necessary to agree how instruction should be communicated during the bunkering operation. In particular, arrangements and signals for emergency stopping of the operation must be agreed. Once all preparations are completed, we are ready to start taking bunkers. If there are any problems with hose connections or valve settings, it is likely that they will show up at the very beginning of the operation. An agreed slow rate should be used when starting so that all connections can be checked for leakage and to see that the fuel is going to the correct tanks. Only when you are sure that everything is as it should the rate be increased up to the agreed maximum rate. Remember, the person at the manifold is in charge of operations at this point, not the supplier. There is no point in taking a sample of the fuel being delivered unless it is a representative sample. There are accepted procedures for collecting, labeling, distribution, and onboard retention of the sample. You should be aware of the requirements for your vessel and follow them carefully. It is recommended that only the correct containers are used for samples, and that the sample is obtained by a continuous drip method, so that it represents the fuel delivered throughout the bunkering operation. This list shows the samples that are required. Click on the buttons to find out more about the samples. It is now a requirement that a sample is taken for MARPOL Annex 6 purposes. The sample has to be specifically for the purpose of meeting the MARPOL regulations. It must be stored securely and retained on board for at least 12 months. The sample should be taken at the ship's inlet manifold, and the sample bottle must be properly sealed on completion. Details of the sample bottle serial number must be added to the bunker delivery note and entered into the oil record book or logbook. There should be documentation on board your ship giving the full requirements of these regulations. Onboard testing is not meant to give accurate results, but should give a rough indication for the main parameter values of the fuel. Typically, onboard testing is carried out using simple test equipment. The parameters that are usually tested are shown in the list. The results from these tests will give an early indication if using the fuel is likely to cause any operational problems. Take the opportunity to do these tests using the fuel on board your vessel so that you become more familiar with them. Many ship operators make use of a specialist fuel analysis service to get detailed information on the quality of the fuel delivered. The major classification societies offer this service and usually supply the containers, labels and instructions for taking and forwarding the samples. The analysis report covers the fuel properties and contaminant content. It also gives advice on storage and handling and predictions on the effect of using the fuel. It is also good practice to carry out onboard testing of the fuel as a check on the accuracy of the shoreside analysis report. It is important that the bunkering operation is closely monitored from start to finish. This not only requires that tank levels are monitored continuously, but also that someone is on station at the manifold to check the hoses, connections and pipelines for any leakage. Tanks should be sounded regularly during the operation, and particularly when topping off and changing over tanks. Even those tanks not being filled should be checked to ensure there is no leakage past valves into them. These requirements should be included in the bunkering procedures laid down in the ship's Safety Management Manual as required by the ISM Code. As part of the bunker plan, there should be clear, detailed instructions regarding the necessary actions for completing the bunkering operation. As the first tanks approach the required level, the valves should be opened for the next tanks to be filled. By controlling these valves, the filling rate of the first tanks can be slowed down. Once the required level is reached, the valves for the first tanks can be shut, allowing the full flow to pass to the second tanks without interruption to bunkering. When the final tanks are close to the required level, the rate should be slowed down to allow controlled topping off. The supplier should be informed and be ready to stop delivery. At completion, all valves should be closed, any blanking plates refitted, and all tanks should be sounded. Quantities can then be calculated and agreed with supplier. You will now hopefully appreciate that it is necessary to closely monitor the entire bunkering operation. Since bunkering operations are the source of a majority of pollution incidents involving fuel oils, it is necessary that every precaution is taken to avoid pollution incidents. We have looked at the various requirements and procedures that are in place to minimize the risk of pollution during bunkering. You should now have a knowledge and understanding of these procedures. Remember, everyone on board the ship has a responsibility to do everything possible to avoid pollution. It is up to you to ensure that you are aware of the requirements and procedures that apply to your ship. After completing this chapter, the learner will know the basic methods used for removing water and dirt from the fuel, know how the fuel is prepared for use in a diesel engine, be aware of the purpose of some of the fuel additives that are available. In the previous chapters of this module, we have concentrated on the storage of fuel on board, and the procedures and systems in place to achieve this safely with a minimum risk to the environment. The condition of the fuel is, however, unfit for use without further cleaning and pre-treatment. In this chapter, we will look at the way in which we can prepare the fuel ready for use in a diesel engine fuel system. The extent of the treatment really depends on the grade of fuel that we are operating with. Distillate fuels require far less treatment than residual fuels. The main purpose of the settling tank is to give time for any water or solids contained in the fuel to settle to the bottom of the tank. The tank is provided with a drain cock, which should be operated regularly to remove as much of the settled water and dirt as possible. This settling or separation occurs due to the fact that the water and dirt have a higher density than the fuel oil, and over time gravitational forces will cause these heavier components to pass to the bottom of the tank. This is a fairly slow process, and even with the assistance of heating, which increases the density difference between oil and water, only the larger droplets of water and heaviest solid particles will settle in the time available. As we will see later, we need to use other means to remove the remaining water and dirt from the fuel before we can use it. The settling tank is usually provided with two suction connections for the pumps that take the fuel from the tank, a low suction near the bottom of the tank and a high suction positioned just above. The valves used for these suction connections will be remotely operated quick closing valves. We have already said that the settling tank relies on a difference in density for separation to occur due to the effect of gravity. However, this is not the whole story. All matter is affected by gravity. An object will fall to the earth due to gravitational force acting on it, which is determined by the object's mass and the acceleration due to gravity. The air resistance results in a drag force, which acts to slow down the rate of fall. The difference between the two forces determines the speed at which the object will fall. Similarly, in the settling tank, and ignoring buoyancy forces, the water droplets and dirt particles are subject to a falling force, and the fuel oil provides the drag force. The size of the drag force is determined by the viscosity and density of the fuel and the surface area of the particle. At increased temperature, the density and viscosity of the fuel oil decreases, and therefore the drag force reduces. The settling tank low suction connection will be used for normal operation. If there is a build-up of dirt in the bottom of the tank, or if vessel movement in rough weather is likely to disturb the settled dirt and water, then the high suction can be used. This will reduce the amount of dirt and water drawn from the tank by the pump. A suction strainer is fitted between the tank outlet valves and the pump inlet to protect the pump from damage by the larger particles of dirt. The suction strainer usually has a coarse mesh to help ensure an acceptable flow to the pump. Only relatively large particles of dirt are removed at this stage. Further cleaning of the fuel is necessary before it can be transferred to the service tank for use in a diesel engine fuel system. This can be achieved dynamically using centrifuges or by using a static filter module. Both of these devices are usually self-cleaning. You will probably have one or other of these fitted on your current vessel. We have seen that a settling tank relies on a difference in density to separate different liquids and solids. This is a slow process due to the fact that there is not much difference in the densities of fuel and water, and so the separating forces are relatively small. To speed up the process, the separating forces need to be increased, and this is the purpose of the centrifuge. The centrifuge usually consists of a gear-driven bowl contained within a casing, provided with suitable inlet and outlet passages. There is only time for a brief description of the operating principles of the centrifuge in this module. A more complete coverage is given in Seagull's ALCAP series of modules. The high-speed rotation of the centrifuge bowl generates forces many times greater than gravitational force due to the centrifugal effect. This increases the separating force between the different components of the mixture passing through the bowl. The heavy components of the dirty fuel mixture, usually solids and water, move to the outer part of the centrifuge bowl. A compact stack of conical discs are used to assist the separating process. The centrifuge can be set up to allow discharge of water and dirt, or to collect dirt in the outer part of the bowl. Most centrifuges are designed as self-cleaning units and have an automatic, timed sludging facility. Click on the buttons to learn about the different arrangements. When a centrifuge is set up to continuously discharge water, it is referred to as a purifier. Dirty oil enters the bowl through a central tube and passes down to the distribution plate at the bottom, and then upwards through the disc stack. The forces generated by the high speed of rotation cause the water and dirt, which are heavier than oil, to move to the outer part of the disc stack and bowl. The water and dirt gather in a region between the wall of the bowl and just inside the edge of the disc stack. The clean oil gathers in the region from the center of the bowl to just inside the edge of the disc stack. The point where the separated oil and water meet is referred to as the interface. The position of the interface is controlled by using gravity discs with different size central holes or gravity plugs of different length. These determine the effective position of the water outlet. The clean oil passes up the outside of the central tube to the outlet to the service tank. The water flows over the disc stack cover plate to the edge of the gravity disc or plug and out through the water outlet. When a centrifuge is set up without a continuous water discharge, it is referred to as a clarifier. The general operating principles are the same as for a purifier, except that the water outlet is blanked off by the top cover of the disc stack. Instead of separating water and solids from the dirty oil, a clarifier separates solids from a liquid mixture. The solids build up on the inner wall of the bowl and have to be removed regularly. As already stated, this is achieved through an automatic sludging cycle. The factors which affect the performance of the centrifuge are the density difference, the speed of rotation, and the time that the mixture is in the bowl. We usually operate with temperatures as high as possible, but below the boiling point of water, to maximize the density difference. Where the capacity of the centrifuges is much greater than the consumption rate of the machinery, then a low flow rate can be used to increase time in the bowl. This also allows us to use two centrifuges in series, one as a purifier and one as a clarifier, which increases the cleaning effect. This is the preferred arrangement where possible. Where capacities of the centrifuges are not much greater than the consumption rate of the machinery, it is possible to use them as purifiers operating in parallel. This allows us to have a reduced flow rate through each centrifuge, but still maintain an overall throughput greater than the consumption rate. The factors which affect the performance of the centrifuge are the density difference, the speed of rotation, and the time that the mixture is in the bowl. We usually operate with temperatures as high as possible, but below the boiling point of water, to maximize the density difference. Where the capacity of the centrifuges is much greater than the consumption rate of the machinery, then a low flow rate can be used to increase time in the bowl. This also allows us to use two centrifuges in series, one as a purifier and one as a clarifier, which increases the cleaning effect. This is the preferred arrangement where possible. Where capacities of the centrifuges are not much greater than the consumption rate of the machinery, it is possible to use them as purifiers operating in parallel. This allows us to have a reduced flow rate through each centrifuge, but still maintain an overall throughput greater than the consumption rate. When the fuel density is too close to that of water, it is not possible to operate a conventional purifier arrangement. There are a number of centrifuges on the market designed to operate as a form of clarifier for treating fuel oils with a density of up to approximately 1010 kilograms per cubic meter at 15 degrees Celsius. During normal operation, if sufficient water separates and collects in the bowl, some will carry over to the clean oil outlet, which is fitted with a water sensor. When water is detected, a solenoid valve opens in the water outlet, allowing a short discharge of water to occur before closing again. We have already mentioned the use of suction strainers to protect transfer and feed pumps from relatively large pieces of solid contaminants from storage and settling tanks. We also need other strainers, often referred to as filters, in different parts of the fuel system to ensure the fuel is clean enough to use and to prevent components from being damaged. The majority of filters used in the fuel system will be some form of metal mesh basket or candle type if they are reusable, and paper or felt types if disposable. Click on the buttons to find out more about the different types of filters and the reason for having them. As the name suggests, a cold filter is any filter which is positioned in the part of the fuel system where the fuel is unheated. The mesh size for a cold filter is usually quite large, since the high viscosity of the fuel when cold would give unacceptable pressure drop across the filter. Cold filters are usually intended for removal of large particles. One factor which limits the mesh size of a filter, and therefore the size of particle that can be removed, is the pressure drop across the filter. The pressure drop is also influenced by the viscosity of the fluid. Excessive pressure drop across a filter can cause the filter element to rupture. You will probably have sailed with systems where the filters have differential pressure indicators, measuring the pressure drop across the filter. These are used as indicators for the need to replace or clean filter elements. As fuel is heated at various stages of transfer and pre-treatment, the viscosity will be reduced. The reduced viscosity allows filters with a smaller mesh size to be fitted in these hot sections of the system to remove smaller dirt particles. These are referred to as hot filters. These hot filters are similar in design to the cold filters, but are generally of smaller mesh size. Fine filters capable of removing very small contaminant particles are needed to protect the fuel injection system components. Fine metal mesh, paper and fabric filters are available for removing particles down to a few microns in size. There are also other fine filters, such as edge filters. Edge-type filters are sometimes found in the inlet connection of fuel injection valves. The filter consists of a machined housing and a close-fitting filter element, typically a plug with sharp-edged channels machined along its length. The small clearance between the housing and element is only a few microns. Flow paths are arranged via holes machined at right angles to internal bores in the plug. Fuel is directed into alternate channels from the inlet bore and passes through the small clearance between the plug and the housing into the adjacent channels. These are connected to the outlet bore. Dirt particles larger than the clearance are trapped at the edges of the element, which can be removed periodically for cleaning. Many of the filters used in the fuel system have to be manually cleaned. The filters are usually arranged in pairs, referred to as duplex filters, with changeover cocks or valves that allow isolation of one of the filters for cleaning while the other remains in use. This avoids interrupting operation when cleaning the filters. Some systems have self-cleaning filters fitted. A common type uses a set of thin plates mounted on a spindle. Each pair of plates is separated by a spacer of slightly smaller diameter. A set of static cleaning blades, which mesh with the plate stack in line with the spacers, are also fitted. Fuel flows through the plate stack from the outside to inside, and particles of dirt are trapped between the plate edges. By rotating the central spindle, the dirt is scraped off by the cleaning blades and falls to the bottom of the housing, from where it can be flushed out or removed manually. There are a number of alternative fuel treatment methods that we should consider. Some of these may be used instead of centrifuges, although in many cases they are used in addition to centrifuges. Some of the leading marine diesel engine manufacturers state that centrifuging is always necessary to achieve the required cleanliness of the fuel. Mechanical homogenizers can be used to break down and disperse contaminants and heavy hydrocarbons evenly throughout the fuel. Most mechanical homogenizers use either grinding or crushing action to achieve this. They are capable of breaking up solids, emulsifying any water present, and breaking up heavy hydrocarbon molecules into smaller structures. These smaller hydrocarbon structures are easier to burn, so combustion is improved and harmful emissions may be reduced. Using a homogenizer should also reduce the amount of sludge produced, so reducing disposal costs. A type which is available today consists of a conical rotor and stator which have slightly different tapers, so that the clearance is greater at one end than the other. The dirty fuel enters at the end with the greatest clearance and accelerates through to the exit end, which has the smallest clearance. You may come across homogenizers fitted in the system on board some of your vessels, usually working alongside centrifuges. Many mechanical homogenizers also generate ultrasonic energy, which assists in the breakdown of some of the contaminants, as well as the heavy hydrocarbons. There are also some devices which rely only on the ultrasonic energy to achieve the breakdown. The ultrasonic energy, which is a form of sound energy, causes the components within the fuel to vibrate rapidly, which results in them breaking down into small particles and molecules. You may have come across similar low-energy devices which are used for cleaning components by shaking the dirt from them. Cleaning of heat exchanger plates can be achieved this way. There are a number of static filter modules available which can be used in place of centrifuges for fuel treatment. The modules are made up of a number of different filters, typically coarse filter for removal of large solid particles, coalescer filter for removal of water, fine filter for removal of smaller particles, and magnetic filter for removal of some iron-based metal particles. These units are more common for service in either distillate fuel systems or lubricating oil systems. It is unlikely that you will find them used with heavy fuel systems unless there are centrifuges also fitted. Many of the static filter systems, just like centrifuges, are provided with a self-cleaning facility to reduce downtime and manual effort. Whereas centrifuges use sludging cycles to remove accumulated dirt from the bowl at regular intervals, static filter units usually use backflushing to remove collected dirt. Through a suitable arrangement of control valves, the cleaned fuel is made to flow back through the filter to a drain sump. This flushes the trapped dirt out of the filter elements. A clean filter will be in line while backflushing of a dirty filter occurs to maintain supply. Water is drained from the coalescer unit by a float-controlled drain valve or other similar arrangement. The treatment we have looked at up to now has been pre-treatment required to clean the fuel. At this point, the clean fuel is delivered to the daily service tank, from where it can be drawn for use in the machinery. If the cleaning process has been effective, there should be very little dirt or contamination in the service tank. Regular draining of the tank is still necessary to remove any carryover or condensation. This should be one of your routine duties. We mentioned in an earlier section the problem of microbial contamination of fuel, and said we would look at how to deal with it later. The condition requires the use of chemical treatment in the form of a biocide. Biocides and other chemical additives are widely available to deal with this and other fuel-related problems. Some of these treatments can be added at the storage stage, but most are designed for use in and after the service tank. We are not going to look at the chemistry of the additive here. That would be of no benefit to you. We will look at what the additives are claimed to do. Remember, as with all chemicals, you must take care and use appropriate personal protective equipment as indicated on the material safety data sheets when you are handling them. You can learn more about these by clicking on the buttons. It is generally accepted that if there is no water present in a fuel tank, there can be no microbial activity. You should therefore make sure that water is drained from fuel tanks regularly. Watch out for the smell of rotten eggs, hydrogen sulfide gas, from the tanks, which will give some indication of the problem. When microbial contamination does occur, you will need to use biocides to kill off and control recurrence of the bacterial colonies. There are many different biocides available, and most are about 90% effective, so repeat treatment is usually necessary. The treatment can cause problems as the dead bacteria fall to the bottom of the tank, forming a sludge, which can be carried into the system, causing further blockage and corrosion. To prevent recurrence of microbes, it is necessary to completely sterilize the system, including all tanks, pipework and fittings. As this is not usually possible on an operational ship, it is best to avoid the problem altogether. Keep checking for water in those fuel tanks. When fuels are in storage, oxidation occurs, which can result in chemical changes to the fuel, leading to sludge formation. The chemical changes can also affect the combustion performance of the fuel. Fuel stabilizers are intended to preserve the condition of the fuel by stopping or slowing down the aging process. If the stabilizer is effective, then the fuel should burn more cleanly and emissions should be reduced. Fuel additives are chemical compounds which are intended to either enhance the performance properties of the fuel or provide properties which the fuel naturally lacks. There are many additives on the marketplace which all claim to achieve these purposes. Some of the most common types of additives are combustion improvers, ignition improvers, detergents, cold temperature gelling preventers, and lubricity agents for low-sulfur diesels. Some of the additives have proven to be beneficial, while others may not do all that is claimed. Other treatments which you should be aware of include inline blending and emulsification processes. With blending, two different grades of fuel, usually a residual and a distillate, are mixed together in the supply line to the engine to produce a blended fuel which is better suited for use in the engine than the individual grades. It is possible to vary the blend ratio to suit operating conditions, for example different engine loads, to give optimum performance. Some engine manufacturers have moved to emulsified fuels, a fuel and water mixture, as a way of reducing the level of emissions. This is normally carried out in part of the engine fuel system after the service tank. It may seem strange to you, after all we have said about not mixing fuels and removing water from the fuel, to see that some engine manufacturers are intentionally doing the opposite. When the fuel is drawn from the service tank, further treatment is necessary to make sure that the condition of the fuel is correct for the intended use. Fuel for a diesel engine, for example, has to be heated to ensure that the viscosity is correct for injection. We saw in the previous section that inline blending and fuel emulsification are also used, normally after the service tank. This further treatment is part of the in-use system and is covered in the module on fuel systems, Seagull CBT number 9. In this section, we have looked at the various treatment processes that are used when dealing with fuel on board the ship. Some of the processes will be in use on board your current vessel, and hopefully you will now have a better understanding of them. You should also now be aware of other treatments, mechanical and chemical, that are available, which you may come across in the future.